Well, we're back from spring break. It's always kind of tough, to get back in the groove of things. But I want to let you know I've been grading the Phase 1 submissions for the design project. I'm about halfway through those to this point, and so far I'm really impressed. Honestly, I'd say this is the best group of submissions I've ever seen in terms of like the logical clarity of the calculations, good level of research. I think every one I've seen so far, there's a couple of things that need to be fixed, but in general, the foundation's really strong, and so I'm happy with what has been achieved on the project so far. A couple of announcements. Homework 4 is due before class on, I'm sorry, not 4, 9. Still, you could tell it's been a long spring break when I don't remember numbers. Okay, homework 9 is due before class on Friday, and then phase 2 of the design project is due a week from today. And that's the one where you're going to take the demand estimation you've developed and translate it into pipe sizing. We'll talk a little bit more about that today, but if you want to begin on phase 2 and you haven't yet got my feedback, you can proceed with the flow rates you've assumed and then make adjustments later. The submission for project phase 2 is simply 2 PDF files, nothing more. They're just annotated maps of your network, and I'll show you what I mean by annotated in just a minute. So today I'm going to demonstrate how to import a background image into WaterGems and use that as a basis for scaled maps. And then we're going to continue talking about specific energy, total energy, and some of the applications that are described in Chapter 12 of the book. So before I get into a WaterGems demo, does anybody have any questions? All right. So let me do that WaterGems demo. There's a tool when you import a background layer in WaterGems. For whatever reason, it may have use compression or optimal loading as enabled. And my experience has been that that causes the program to crash. And I don't know if it's just because we've got a relatively large background image that's being imported. I don't know what the issue is, but turn those off to avoid the crash. So you'll see that I already have the connection client running, and that's required in order to start WaterGems. So in the file of the project file in Blackboard, there's this TIFF file here, TIF, scaled map import to WaterCAD. And so what I'm going to demonstrate for you is how to bring that in the background and then how you could just kind of draw on top of it, and then you wouldn't have to enter user-defined lengths anymore. There it is. All right. So I'm just going to create a new hydraulic model, and if I was actually going to be doing the modeling, then I'd need to make sure that the friction loss method is set to Darcy-Weisbach instead of Hayes and Williams. And then the other key thing, especially in this case, is we want to make sure that it's assuming the SI units. So if you look down at the bottom, see how it says X and Y is in units of meters? That's good. That's what we need. So background layers. This location here, we're going to click on the new. So it's like a white sheet of paper, new file. And then I'm going to browse to the location of that TIFF file. It was this one, scaled mat import to WaterCAD. I think yours may be named something slightly different, but basically if you were going to open this just like with Paint or something, it's a TIFF file that you can open with a lot of different programs. It just looks like a, I'll open it with Paint. It's our network. You've got a very similar map. I think the only thing that's different is it doesn't say Spring 2022 on yours. But the number of pixels and the scaling of it, I've intentionally scaled this so that each pixel is 1 meter. And so the way we're going to test that is if you were going to draw a pipe that's this long, which in printed space is 1 centimeter, that should be 100 meters if you draw a pipe on top of that line and it's scaled correctly. So what we're going to do is import that TIFF file here. So I did background layers, new. Now I'm just browsing to the location, open, and then turn off, use compression, optimal image loading mode, which is like such a misnomer since it crashes the program every time. It's not optimal if the program won't run. But what this is doing is it's telling you it's a mapping between like the image space and the real world space. And so I'm telling it, for example, that 1 pixel is equal to 1 meter by the X and Y coordinates of each corner of the image. So it's just the default because I've already scaled the image so that 1 meter is equal to 1 pixel. Click OK and it'll bring this image in the background, which I may have to zoom to the extents to see, and there's our map. So in your case, what you're going to do is create a network where you've got a reservoir somewhere up on the hill, who knows where. You know, that's an optimization problem you're going to have to play around with. So you drop the reservoir, and then you start to do junctions at different places. You know, how to connect the dots most efficiently, that's the question, one of the questions. But to make sure it's scaled correctly, let's draw a little pipe from here to there. And if I bring up the properties of that pipe, it should tell me that it's pretty close to 100 meters. So see over here it says scaled length 99 meters. Good enough. Based on where I clicked, good enough. So the nice thing is that now that I've drawn this network on top of the scaled map, then the pipe lengths have the actual physical length that they will be in the real world. So from B to C, for example, it's telling me that pipe is 699 meters. Great. So I don't have to go into the flex tables for these pipes. I don't have to use user-defined lengths anymore like we have when we've used the program in the past. Now it's just the scaled length that here, length scaled, that we can rely on. So any questions about that? So when you're printing your network map for phase 2 submission, turn off the background layer because otherwise it won't be possible to see things correctly. Like the image in the background will kind of be concealing the attributes of what I do want to see. So any questions so far on the water gems? Yeah.
Do we have access to this file?
Yeah, I think so. Let's check. You didn't see it? It's possible I need to upload it, but I thought that I'd done that in the project folder.
There's the PDF.
The PDF, but not the TIFF? All right. Let's just double check. And if not, I can upload it now. Although it'll say 2022, don't let that throw you off. I did create a new one for this year. So project. Yeah, it doesn't seem to be there. All right. Thanks for noticing that. So I'm just going to put it right here. Upload. Scaled map. This is the one. All right. So it's there now. Visible. Okay. So here's an example of a submission that a student provided from a couple of years ago. And when I say annotated, that just means with notes on it. And the notes that I want on your map are things like the length of the pipe, the diameter of the pipe, the flow rate through the pipe. Here at junctions. So look at junction A. It's got the pressure of the junction and the flow rate that's coming out at the junction. So you get an idea of the annotation. This person did a really nice job. Like the symbol sizes are appropriate for the size of the network. You know, like if the text was a lot bigger, then the text would be too large. And if it was much smaller, then it would be difficult to read for the scale of the network. So the sizing, the placement are appropriate. There's nothing where, like, the annotation is on the line and therefore more difficult to read. What this student didn't do is a good job optimizing, like, the physical locations of the pipe. So take, for instance, this location D. There's no water being extracted from junction D. If you remember the network map, let's see, do we have it here still? There's no green arrow at this location, so there's no reason to have a pipe there if no water is being extracted from that location. This corner boundary just is like the limits of the east zone. So you only need to provide water to the location of the green arrows, and so there's no reason to have the pipe going from C to this corner edge and then down to E. You could have a shorter pipe if it just went straight from C to E. So the point is, this person did a great job with the annotations. I'm really happy with that, but the pipe locations aren't well optimized in this illustration. Yeah?
So when we do this, if we have like the map as an overlay and then put all the pipes on it and delete the map with like the annotations and stuff after, it won't affect the actual pipe system, right? Like the image is like a still image, it doesn't get affected by it?
Yeah, yeah. So adding the annotations doesn't affect the image. You can turn it on and off as you need as a reference. Yeah. There's 2 maps that you need to upload. So why do you think I want 2 maps? It's because I want to see how the system is performing under 2 different conditions. I want to know what are the pressures in the network when you've got the design flow. So when you're extracting that maximum flow rate from each of the green arrow locations, that's one of the maps, is show me the network performance under the design condition. And then the other map that you upload is you have to go back into the junctions, turn off all the demands, and then show me how is the system performing under static conditions when there's no demand. So what's the maximum pressure under 0 demand, and then what's the minimum pressure under the design condition. And so then that will illustrate the system's performance under the 2 extremes it's likely to encounter. The overnight condition when nobody's using any water, and then the design condition, which may only roll around occasionally, that there would be both a fire and a stadium event, and they're watering at the golf course and the residential areas at peak demand. So all those things are assuming they happen simultaneously. We want to have a network that's robust enough to maintain the minimum pressure of 240 kilopascals at every location in the network when that occurs. So, therefore, 2 maps. Other questions? Yeah.
Yeah, so for like revisions we need to make, do we just use the new numbers, or do we need to upload new calculations or something?
So revisions to demand estimation.
Yeah.
That's what you mean. When you submit the final submission at the end of the project, that is when you show me what are your revised, like you prove to me your improvements and revisions on demand estimation then. Just go ahead and use those updated flow rates in this part. Other questions? All right. So, I was impressed with what had been done in phase 1. Let's keep the momentum going. Stop by, ask me if you've got questions. If you feel uncertainty about what you're supposed to be doing on phase 2, let me know how I can help. All right. So let's talk about specific energy and get back into the mindset of water flowing through open channels. So remember that a specific energy diagram like this has on the horizontal axis specific energy, which is depth plus velocity head. That's specific energy. Those 2 things added together, depth plus velocity head. Vertical axis is the depth of flow, and so minimum specific energy is this leftmost point on the curve where the amount of energy is not changing with depth because it's, the curve itself is vertical at this leftmost point. Now, think about some irregularly shaped channel, or it could be a regular shape, but even if it is irregular, when we've got some incremental change in depth, dy, then top width b, and if it's a very small incremental change in depth, then the top width b is approximately equal to the bottom width of that differential element. And so dA, the differential area, is just the top width b times the dy, the change in depth. So Froude number, remember, is a way that we've talked about on prior occasions how we can classify the flow regime. Flow regime being supercritical or subcritical. And a Froude number of 1 is when conditions are critical. And so, like, where does this formula come from? This formula that we can use regardless of the shape of the channel. We can use this to diagnose the flow regime, to determine whether conditions are supercritical or subcritical. So just briefly, where we get this formula is by looking at specific energy. So specific energy, recall, is depth plus velocity head. And here, we're expressing velocity head in this way of saying, instead of just v squared divided by 2g, we're saying q squared divided by 2ga squared. And in this case, doing that allows us to substitute in the expression of dA dy on the right-hand side, and on the left-hand side, dE dy. So the change in energy with respect to depth. So this leftmost point, where there's no change in specific energy with depth, where the slope is vertical, we're setting the left-hand side of this equation equal to 0. And so if we just rearrange this, then, and of course the top width b is dA dy. So for some irregularly shaped channel, dA is b times dy. So therefore, b is dA divided by dy. So this idea of the Froude number being equal to 1 under critical conditions, this expression q squared times b divided by ga cubed is just from taking the derivative of the specific energy equation. So that's important to us in a lot of cases when we need to either diagnose the flow regime or we want to know something related to it. So for example, what would be the slope that gives us critical conditions for a certain channel? So here, the Froude number is equal to 1. We can rearrange that equation and it'll look like this. So this is what we would use to determine the critical depth for any kind of a channel, whether it's rectangular, trapezoidal, triangular, circular. Regardless of the shape, you can use this formula to determine the critical depth. And just as an illustration of how you'd use it, let's say that we had a rectangular channel that is 4 meters wide. And if it's 4 meters wide and it's rectangular, then that's both the top width and the bottom width. And we're putting a flow rate of 10 cubic meters per second through that channel. We want to know what is the critical depth. So we could use this formula to find the critical depth. And so area, when conditions are critical, A sub c is going to be 4 times yc. So 4 is the width, yc is the unknown critical depth. That gives us the area when conditions are critical. B sub c is the top width when conditions are critical. And here, the top width is staying the same regardless of whether it's critical or not. It's 4 meters. So if we want to find out what is the critical depth, then we'd have q squared divided by g equal to a sub c cubed divided by b sub c. So that is then 10 cubic meters per second squared divided by 9.81 meters per second squared is equal to AC. So that's 4 times yc cubed divided by BC, which is 4 meters. So If we use our solver on that, we'll get on the left-hand side 40.77. And on the right-hand side, 64 YC cubed. In fact, I don't think we even need to use the solver here. We can just calculate it directly that the critical depth, Y sub C, is 0.860 meters. Let me just bring that up on the screen here. Okay, so we're putting 10 cubic meters per second through a 4 meter wide channel. The critical depth is 0.860. So what does that mean? If we observed 1 meter of water depth, then conditions would be subcritical, because any depth that's more than the critical depth is going to be associated with a slow-moving velocity and therefore subcritical conditions. If we observed a depth of less than 0.86, then that is associated with supercritical conditions. And so this is another way to diagnose the flow regime, is either you can calculate the Froude number for the depth that you observe, or you can calculate the critical depth, and then any depth greater than that would be subcritical conditions, any depth less than that would be supercritical conditions. But this formula is always applicable regardless of the channel geometry. Now, there is an easier formula than this, which we can use, but we can only use it when we've got rectangular channels. So here's a warning, is don't use this approach for anything other than a rectangular channel. The idea of flow per unit width only has meaning if the channel is rectangular. So this example, we had 10 cubic meters per second flowing through a channel that's 4 meters wide. So the flow per unit width, lowercase q is big Q divided by B. So that's 10 cubic meters per second going through a channel that's 4 meters wide. So what that means is that there's 2.5 cubic meters per second per meter of width. So what we're saying is, let's divide this up into sections, and how much flow is going through each of those 1 meter sections. 2.5 meters squared per second is how we could express that, the flow per unit width. So obviously, if you had water going through a semicircular channel, it's not going to have the same physical meaning here, because a meter of width here has less flow area compared to a meter of width somewhere else. So don't do flow per unit width if you've got a trapezoidal channel, because it's the same problem. In the case of a trapezoidal channel, not every meter of width is the same, because maybe the meter that you're looking at includes the side on the left or on the right. So for a rectangular channel, you can calculate the flow per unit width and then determine the critical depth by lowercase q squared divided by g to the 1/3 power. So we just worked this example where it was 4 meters wide. It is rectangular. So how would we use this to find the critical depth here? So y sub c is lowercase q squared divided by g to the 1/3 power. So we had, the lowercase q is 2.5 meters squared per second, and we square that, divided by 9.81 meters per second squared to the 1/3 power. So in our previous example, we got that it was 0.86. Let's put that to the test here. Get out your calculator and see if we get the same depth. 2.5 squared divided by 9.81 power of 0.333. It works. That's a simpler way to find the critical depth, but only use it if conditions are, if it's a rectangular channel. It's a nice little simplification that we will sometimes use. So any questions about Froude number, specific energy diagrams, critical depth? Anybody have any questions before we move on? All right. So let's say we've got a rectangular channel. Those are more complicated. And I think it's table 10.1 in your book has the geometric properties, for example, the top width, the cross-sectional area, wetted perimeter, and so on, like how you can calculate it. So critical slope is another way that you can diagnose flow regime. You know, like if you've got water flowing through a channel where the slope is greater than the critical slope, then that means you're going to have supercritical flow. Or if the slope is less than the critical slope, then you'll have subcritical flow. So let's say that we have this trapezoidal channel, which is 3 meters wide at the bottom. It's got 1.5 to 1 side slopes. And so when it says 1.5, that's the horizontal, and the vertical is 1. And so remember, T is talking about the horizontal component when you've got a assumed vertical of 1. So here, T is going to be 1.5. And it's carrying a flow rate of 186 cubic meters per second. So we're going to find the critical slope by doing 2 different steps. First of all, finding the critical depth using this expression. So find out what is the critical depth. And then once we know the critical depth, we're going to use Manning's equation to find out what is the slope associated with that. And here, the n value that you should use is 0.013. So it's concrete. That defines the n value. So the first thing is substitute all of these parameters. For example, calculate W, because we know T, so calculate W. And once you've got W, you can calculate the top width B as a function of the bottom width B, which is 3 meters, T, and Y. Y is unknown. So substitute everything into this, and Y will be the only unknown, and then solve for the critical depth. So I'm going to pause the recording. While you're doing that, while you're solving for the critical depth, I'm going to return the quizzes from before spring break. So I'll be circulating around. Okay, so we're going to use this formula, and Q is 186, uppercase B is lowercase b plus 2ty, so that's 3 plus 2 times 1.5 times y, so 3 plus 3y. And then A is 3 plus 1.5 times y. So if we write it out, it looks like this: 186 squared, 3 plus 3y in the numerator, then in the denominator g, and area cubed, where area is 3 plus 1.5 times y, and then that's cubed. So putting this into either your calculator or Excel or Wolfram Alpha. So in Wolfram Alpha here I wrote it out as q squared times, this is b, 3 plus 3y, and then the denominator g area cubed is equal to 1. Solve for y, and it gets that y is either negative 1, which we don't care about, or 4.12, and that's the right answer. So y sub c is 4.12 meters. That's the critical depth through this channel. So that means that if we send 186 cubic meters per second through this channel, and we have it set at the critical slope, then the depth would be 4.12 meters. That's the slope that would cause it to flow at 4.12 meters. Now, we haven't found that slope yet. That's going to be part 2 of what we're doing. But this is the scenario that, if we had a steeper slope, then the water would move at a higher velocity, the depth would be less than 4.12, and conditions would be supercritical. If we had what's called a mild slope, which means less steep than the critical slope, then the depth would be greater than 4.12 meters, and conditions would be subcritical. So any questions so far on how we used these geometric parameters here? I guess we didn't end up needing W in the after all, because wetted perimeter isn't one of the terms that goes into this Froude number equation. But any questions so far on how we found the critical depth? All right, so part 2 is now using that critical depth that we've found, let's put it into Manning's equation, where the only unknown, we will need perimeter now. We're going to need it in Manning's equation. The only unknown in Manning's equation is going to be the slope, because Q is 186, area is whatever area is related to 4.12 meters. Wetted perimeter is whatever wetted perimeter is related to the side slope that we've defined, as well as the depth of 4.12 meters. So let's do that. I'll pause again. You solve Manning's equation to find out what is the slope associated with this critical depth. So on the whiteboard, I've got written out how the wetted perimeter is 17.858 meters. The cross-sectional area is 37.837 meters. That is for the critical conditions. So what we're going to do is putting it into Manning's equation, where I've rearranged the formula to be in terms of slope. So we can algebraically rearrange Manning's equation to be in terms of slope, and this is what it looks like. So S is the n value times the flow rate divided by area, hydraulic radius to the 2/3 power, and squared, where hydraulic radius is area divided by wetted perimeter. Or, we could put it into Wolfram Alpha again, just solving for S, where this is what we know so far. Let me try that. So we'll start off with a new one here. Okay, so the flow rate is 186. is equal to the area to the 5/3 power, and we just calculated the area is 37.837 to the power of 5/3. Slope times slope to the 1/2 power, where slope is going to be the unknown that we're solving for. And then oh darn it, divide that by n, so that's 0.013, and times the wetted perimeter to the 2/3 power. And wetted perimeter we got was 17.858 to the power of 2/3, 0.666. Okay, and ask it to compute for S, and it tells us that it is 0.15%, so 0.0015, so that's 0.15%, and that's the same that I had got previously here. If we substituted in to Manning's equation, 0.15% is the critical slope. So that's the slope that would cause the water to flow at the critical depth. And so if we go out there in the world and the slope is greater than that, we'll have supercritical flow conditions if it's 186 cubic meters per second going through this trapezoidal channel that we've got. And if the slope is less than the critical slope, then conditions are subcritical. So, specific energy diagrams tells us how we can find the alternate depths that have the same amount of specific energy. We can also use this diagram to understand how the water behaves when there's some sort of an obstruction or a choke or a transition that's causing non-uniform flow. So if we had the same amount of water going through a river that has a certain width, but it's very steep, then we'd maybe see rapids. So, here you can see some white water that's associated with high velocities of the flow, and that would be for a steep slope. Whereas if we had the same amount of water going through a river channel that has the same width and the same roughness, but the slope is less, then we might see subcritical conditions. The point is that it's the slope that is going to cause variation in the flow depth for a certain flow rate and a certain channel width and a given n value. It's variations in the slope that cause those different specific energies. Now, we can apply the same specific energy analysis to look at what happens when water flows off of a drop. So here you can see delta Z is associated with water going down from a drop. Now, it's very important to notice here that prior to the drop, conditions were subcritical. Now, how can we know that conditions were subcritical? It's because they've visually represented what is the critical depth, and the actual flow depth before the step was more than the critical depth. And so from this, we can see that the flow conditions were subcritical upstream, and then downstream, they're going to remain subcritical. The interesting thing is that by having the water drop off of this step, that's actually increasing the depth downstream. And we wouldn't necessarily know that unless we analyze the specific energy diagram. So bed transitions like a drop, we can determine the flow regime upstream, and it's going to maintain the same flow regime downstream. So we could have calculated the Froude number at 1, or we can just diagnose it on the basis of the flow depths. But look at what happens with the specific energy diagram. Water's flowing with a certain amount of specific energy at 1. So this 1 line is just showing if we reflect the given depth at location 1 off of the specific energy diagram, then there is a supercritical route, but instead what we're doing is going down to intercept the horizontal axis, and you're increasing the amount of specific energy with a drop down. So the water is gaining energy by flowing off of that step. So that pushes the specific energy diagram to the right. And then we're going to go up, and intercept the specific energy diagram, and there's two routes. There's the supercritical and the subcritical, but since it was subcritical before the step, it's going to stay subcritical. So you can find out what the new depth is by looking at the specific energy diagram. So again, to summarize, you start with this initial depth, go down to find out the amount of specific energy. You increase the specific energy in the amount of delta Z, which is the step distance, and then you find the subcritical route, and that would give you the new depth downstream. All right, we're out of time for today, so we'll pick up here when we get together on Wednesday.